at reciprocals of linear functions. So if you remember, what is a reciprocal? Well, a reciprocal are any two numbers where their product is 1. So 1/2 times 2 over 1, right, is 2 over 2 is 1. If I have -3, if I multiply that by -1/3, right, multiply numerators by numerators, I get +3, denominators by denominators, +3, reduces down to 1. So notice all I do is I flip my fraction and I keep the sign the same, right? A reciprocal does not swap the sign. I need those signs to cancel out to become +1. So for any number a, its reciprocal is 1 over a. Right? And again, if I already have a fraction, 2/3, its reciprocal is 1 over 2/3, right? Which is 3 over 2. It's that kiss and flip idea. So we're going to talk about reciprocal functions, right? So if I have some function that I call f of x, its reciprocal function is going to be 1 over f of x, where f of x for us in this course is going to be something linear or something quadratic, our two favorite types of functions in 20-1. What that means is that every single x value I put in, instead of spitting out the y value that it should, it's going to spit out the reciprocal y value, or 1 over y. So if I say x is some number, right, when I plug it into my function y, right, it'll spit out some number. Again, I don't have an equation here, but if I put in the number 1, what's going to happen is if I put in the number 1, well, my reciprocal is 1 over 1, which is just 1. If I put in 2, my reciprocal is 1 over 2, or 1/2. If I put in a negative, like -5, my reciprocal is -1/5. If I put in a fraction, like 1/3, my reciprocal is 3 over 1, right, or just 3. If I put in -1, well, now I do -1 over 1, which is also just -1. If I put in a really big number, the result is that I get 1 over that really big number, so a really small number. And if I put in 0, what happens is I get something that has division by 0. It does not exist. I have a non-permissible value. Right? I can't have a 0 in my denominator. So here are some things that we can come to the conclusion of when I take the reciprocal of a function. So the reciprocal of positive and -1 is still positive and -1. These are what we call invariant points. Because even when I change the function from f of x to 1 over f of x, if the coordinate doesn't change, it doesn't vary, right? I call that an invariant point. So that happens when y is plus or minus 1. The reciprocal of 0 does not exist. So that's taking 0 on my original function and flipping it to my reciprocal function. When I think about 0 on my original function, what that means is that x-intercepts in my original function turn into non-permissible values in my reciprocal function. Because when I have a value of 0 in my original function, that is an x-intercept, right? That's a y value of 0. But when I have a denominator of 0 in my reciprocal function, that's what a non-permissible value is. When I take the reciprocal of small numbers, right? So like this one here, where I took the reciprocal of 1/3, the result was bigger. So f of x small turns into 1 over f of x bigger, right? So it will take small numbers. When I say small numbers, I mean these fractions here, right? A less than 1, a being the number I'm taking the reciprocal of. It's going to get bigger. And when I take the reciprocal of big numbers, so f of x is really big. So for example, my 1,000 here, right? When I took the reciprocal of 1,000, the result of that was a really, really small number. 1 over f of x is smaller. So that's going to help me be able to sketch these graphs and think about the trends of what's happening to my y values, right? Because x, my independent variable x, I'm going to go back to this part here. My independent variable x is something I'm allowed to choose. So I can choose the same x, talk about the same x value, and have no change between my two functions. What I'm looking at is the result of changing that x, right? My dependent variable changing because of the x I put in, because of how the function describes it. So I'm concerned about my y values for all of these things. So let's look at a basic reciprocal function. I'm looking at the linear equation 2x minus 4. So if I take the reciprocal function, all I do is I'm taking the whole function, right? This whole thing is f of x, and I'm going to put that in my denominator. So I'm going to put 2x minus 4 as my denominator. We should know from our rational unit here that 2x minus 4 cannot have a value of 0. That's my non-permissible value. And so I can solve this little equation, this not equal to specifically. And so that's just a reminder that x cannot have a value of positive 2. Because if I put a positive 2 in here, 2 times 2 is 4, minus 4 is 0. I don't know how to do that. So what does this function look like? Well, I know what f of x equals 2x minus 4 looks like. I know that's a linear function that has a y-intercept at negative 4, right? Because this is in slope-intercept form. This is my rise over run. This is my y-intercept. So I can sketch any linear function by starting at that y-intercept and saying for every 2 units I go up, I go 1 unit over. 2 units up, 1 unit over. Right? Or I could go backwards. If I go 2 units down, as long as I counteract that and go 2 units left, that's another point on my graph. So all of these points would be points on the line. Did a bad job there. Points on the line. There we go. Of y equals 2x minus 4, right? Or f of x equals 2x minus 4. This graph has an x-intercept at 2, 0, it looks like. It also has a y-intercept at 0, negative 4. And it has a bunch of these coordinate points, right? So if I talk about f of x, right, I have a bunch of coordinates here. When x is 0, y is negative 4. When x is 1, y is negative 2. When x is 2, y is 0, right? Those are all just the coordinates, the points along this graph. When x is 3, y is 2. Right? And so if I think of the reciprocal function, what's going to happen is that all of these y's are going to turn into reciprocals. So when x is 0, 1 over f of x is negative 1/4. And when x is 1, 1 over f of x is negative 1/2. When x is 2, 1 over f of x does not exist because my original function had a y value of 0, right? And 1 over 0 does not exist. Then I get a positive 1/2 if I had a few more points here, right? 4 or 5, let's keep going. When x is 4, again, I'm just looking at the coordinate of this point. When x is 4, y is 4. When x is 5, y is 6. So notice the trend, as my y values get bigger, right, as I go down this way and they increase, my reciprocals are actually becoming smaller fractions, right? 1/4 is smaller than 1/2, and 1/6 is smaller than 1/4. And so here is what this graph looks like. My reciprocal function, I'm going to focus on this part first, this non-permissible value here. And the way I visualize that on a graph is by what we call a vertical asymptote. So this is my vertical asymptote. And it's kind of like a fence, right? It's a value that, because I'm not allowed to ever have that value on my graph, it's a line that my graph now can't cross. Because if it crosses that value, that means at some point it was equal to that value. And I'm going to give it an equation. I'm going to say x equals 2 because it's a vertical line, just like our axis of symmetry for the quadratic functions unit. And so this is not part of my graph. This is a part where my graph can't be, but I draw it in as that dotted line to help me visualize it. And so now I can sketch some of my other points. When x was 0, y was negative 1/4. So it's going to be like almost here at the axis. When x was negative, or when x was 1, y was negative 2. So when x is 1 here, y is negative 1/2. It's not a super nice point here, it's a 0.5, but I'm going to put my invariant point here. Because I know that when y is negative 1, right, and I'm looking along this y-axis, or this y line here, when y is negative 1, I know that the reciprocal is going to match. So I think those are about, just based on the function, I think that's at about 1.5. Y is negative 1. So 1 over negative 1 is still negative 1. So that's where they meet up. And then I get to my non-permissible value. I jump over to the other side. When x is 3, y is 1/2. Oops, sorry, that's at 1. Right, so I went halfway up, just barely. When x is at 4, y is at 1/4. So I'm really barely off the line here. Then I'm at 1/6, even harder for me to draw. And so sketching these graphs is not so much about getting nice exact points as it is understanding those trends. And so I have another invariant point here because I know that when I now have a y value of positive 1, these graphs will have the same function. And it looks like that's at about 2.5. So 2.5, I had a positive 1. So I have a positive 1 when I take the reciprocal, because the reciprocal of 1 is still 1. It's the only number that does that. 1 and negative 1 are the only numbers that do that. And again, this graph doesn't show them very well, but those are my, what I call, I'll write it all the way out, those are my invariant points. What I'm going to do from this point is I'm going to recognize kind of the trend that's happening. So these numbers are going to increase and they're going to keep increasing. Because in this tiny segment, it's really hard to see here, this tiny, tiny segment, those y values are going to be smaller and smaller fractions. So what happens is when I flip all of those tiny fractions in the part I just highlighted, they're going to give us really big numbers. Right? At some point in here, there's like a tiny little decimal value that has some y value of like 0.01. So when I flip that, when I take the reciprocal, it's going to give us some y value that's 1 over, or 0.01 over 1. It's going to give us 100. So it's going to shoot up towards really, really positive y values. So that's how I can draw kind of that trend in there. So I see that I'm curving up and I kind of hug that asymptote. What's going to happen on the other side is I'm going to curve down and I'm also going to hug what I have as a horizontal asymptote. So I actually have a dotted horizontal line here too. And this is not because of a non-permissible value, but this comes from the fact that if I have a fraction and my numerator is 1, the only way to ever get a y value of 0 is to have a numerator of 0. And if I can't turn 1 into a 0, which I can't because there's no variables up there, I can never have y equals 0. So I just have another asymptote. This is called a horizontal asymptote. And so my graph is just these two curvy purple lines where I connect them, I hug them up to the asymptotes, They go on forever and ever and ever because my original graph has a domain of all real numbers. It goes on forever and ever and ever. But it's that little, and all it is, right? I know there's a lot of like bonus stuff on here. These two purple lines together are the function y equals 1 over 2x minus 4. Right? And if I was to look at this graph without all the extra funky stuff going on, I would just see something that looked like these two portions here. And that's one graph. It just has two separate segments. So my NPV was that x cannot be 2, right? That came from my denominator. I would say the equation of my vertical asymptote is x equals 2 because those are referring to the same thing. My non-permissible value is represented visually by a vertical asymptote. Right? That's what an NPV does on a graph. And when I look at this graph is going to go on forever and ever and ever. So what I'm saying here when I talk about the end behavior is if I look at the left side of my graph, as x goes further and further and further toward really, really small numbers, y actually gets really close to being 0, right? It's never going to be, right? Because these are going to be big numbers. Like if I think about this point here, I had -2, -8. The reciprocal point on my other graph at -2 is going to be -2, -1/8, right? -1/8 is already a pretty small decimal. As I keep getting further, I'm getting closer and closer to 0, but I'll never reach 0 because I don't have a 0 in the numerator. And then on the other side, I notice the same thing. As I pick really, really, really big x's, I also get really, really close from the other side. Right now it's coming down from the top over here. But like some of these points, if I pick this one, right, 7, 9, that was not actually a point on this graph. If I pick a point like 6, 8, right, the reciprocal is going to be, 6, and then 1 over 8, right? So again, getting closer and closer and closer to 0, but I'll never be able to reach 0. So this is what tells me about a vertical asymptote. This behavior, the fact that both of these are approaching 0, is what tells me a horizontal asymptote. And this is the beginning ideas of calculus when we eventually get there. So what a vertical asymptote is, it's a non-permissible value for x that our function can't exist at. So that's our first reciprocal function. We're going to analyze a lot of these, mostly graphically, because we've already done our rational functions unit. So if I look at the next one, if I look at the graph y equals -1/3 x plus 2, it's really helpful for me to think about what happens at my linear graph first, and then how that can help me sketch my reciprocal graph. So if I'm graphing the reciprocal function, what I'm looking at is y equals 1 over -1/3 x plus 2. And I can leave it just like that. I don't need to do anything fancy to this equation. What I'm going to do first is I'm going to sketch my original function. Right? So for me, I'm going to graph y equals -1/3 x plus 2. Just that nice linear function. Because that's going to help me make sure I know what my reciprocal function looks like. I don't need both, right? I don't need to draw this line to be able to draw the other one. It's not part of the same graph, but it can help me sketch it. So again, I'm going to start at my y-intercept, +2. This has a slope of -1/3. So for every 1 unit I go down, I go to the right 3. Or if I'm going up 1 unit, I'm going to the left 3. Right? Rise first, my y values run, my x values second. So up 1 over 3 to the left, down 1 right 3. Connect it as best as I can. Oops. There we go. And so this is y equals negative 1/3 x plus 2, right? This has nothing to do with my reciprocal function, but it also has everything to do with my reciprocal function. So a few things that are going to be key points that I'm going to sketch first. I know my vertical asymptote happens at the x-intercept. So that's the vertical asymptote on 1 over f of x. Happens at the x-intercept on my linear or quadratic function. So it looks like my vertical asymptote here is going to happen at the x-intercept of, it looks like I have the point 6, 0. So my vertical asymptote is going to be at x equals 6. Because 6 is my non-permissible value here, if I take negative 1/3 x plus 2 and say it cannot be 0, and I solve for that, negative 1/3 x equals negative 2, x equals positive 6. So I'm going to dot that dotted line. I'm going to find x equals 6. I'm going to sketch in my vertical asymptote. Oops, at x equals 6. I'm going to put my horizontal asymptote at y equals 0. And for us, our horizontal asymptotes are always going to be at y equals 0. We'll start to explore more difficult rational functions next year in 30-1, where that horizontal asymptote starts to move. So y equals 0. The next points that are nice for me to sketch are my invariant points. And remember, those are at y equals plus or minus 1, not x. I'm looking for a y value of 1 and a y value of negative 1. And wherever my function exists, that's where my reciprocal function will exist as well. Right? Because that's the only value where if I flip my y term, it's not going to change at all. And then from there, the last part I kind of just describe as trends. So for really small x or really small y values, I'm increasing. So when I'm saying that, I'm talking about these segments here, where I have really small y values that are between 0 and 1, or between 0 and negative 1. So those are really small. Their reciprocals are going to do the opposite and get really big. So I'm going to see it go the opposite direction. They go away from each other. As that highlighted portion gets closer to the x-axis, my reciprocal graph is going to get farther away. And then on the other side, my reciprocal function gets really small. So if I'm looking to the left here, right, as I move over to the left, my y values are increasing. They're getting further away from 0. So my reciprocal values are going to get closer to 0. It's basically just going to hug those asymptotes every time. I'll do the same thing on the other segment of my graph. That little highlighted portion is getting close to the x-axis. So my reciprocal portion will get further away. On the right side, my blue arrow here tells me that it's going to continue decreasing forever. So I'll make my y values increase on my reciprocal graph. And so these two purple lines together make the function 1 over negative 1/3 x plus 2. And so again, it's not about a lot of plotting exact points, right? It's about understanding the ideas and the characteristics and how these trends are changing from one type of graph to another. How it's like a transformation, basically, of a linear graph to this curvy, weird reciprocal graph. So if I gave you a graph, you can tell me the equation, right? Because we know all of those things are still true. If I have a reciprocal graph, and here's a really good example of one without all kind of the mess. Notice I don't need that linear function. I want to find the equation of the original linear function. And so it's going to be the same steps that I just had, right? I'm going to look and I'm going to remind myself that my x-intercept on my linear function is equal to my vertical asymptote on my reciprocal function. I'm just going the opposite direction now. Notice that my reciprocal function doesn't have an x-intercept, but it has a vertical asymptote at x equals 2. So what that tells me is that my reciprocal graph is going to have a point at 2, 0. Right? Because on the reciprocal graph, on the red graph we have there, that point is to 1 over 0, and so it does not exist. That's why the vertical asymptote is there at 2. I also know some other points. I can do my invariant points in the opposite direction as well. So I know that when y is 1 and when y is -1, these graphs will meet. Now, it doesn't look like it's a nice x value. It's some decimal values around 2, but I can still plot points there because I know my graphs will have to meet at those 2 points and only those 2 points. So that's at y equals plus or minus 1. And then the last thing is they give me a nice coordinate here. They have 3, 1/3. And that's the idea that I'm taking some xy and I'm turning it into x 1 over y. So the point on my reciprocal graph, or my original graph, again, reciprocals go both ways, that 1/3 flips to become a 3 over 1, right? Or just a 3. So 3 over 1, if you're not sure where that came from. So I can plot that point, again, on my new graph. I can find the point 3, 3. That gives me more than enough to connect my line. That also gives me more than enough to find an equation. Remember, we find an equation of a linear in y equals mx plus b form. So I can find my slope here, right, my m, by picking any 2 points and counting my rise and my run. So if I'm going up by 3 and over 1, then my slope is 3 over 1. So y equals 3x plus b. And I can find my y-intercept by either, I can just keep sketching and make sure it's accurate using that slope. So down 3 over 1, down 3 over 1, and find out it's at -6. I could also plug in any point on my graph. So I have that point 3, 3. I could say 3 equals 3 times 3 plus b and solve for that. Right, so 3 equals 9 plus b, subtract 9 from both sides, -6 equals b. So the linear function that causes, that when I take the reciprocal, is 3x minus 6. So that's the equation of my blue graph here. That means the red graph here is the equation, and you could plug it into a calculator to check. Y equals 1 over 3x minus 6. So there's one more for you to give a try. Same idea here, right? I'm going to go in that same order. First thing, my x-intercept is my vertical asymptote. So I know I have a point. In this case, at -1, 0. I'm also going to plot my invariant points. So again, I'm looking along, I'm just saying, where does my graph exist when y is +1 and when y is -1? And so I find those points where those functions hit those, right? If I zoom in really close, they're not nice numbers, right? But I'm on -1 and +1. So that at least gives me enough to be able to sketch that pretty accurately. I would like to have this other point just so I have a nice exact point. And remember, I'm always keeping my x value the same, and then I'm flipping my y value. Sign stays the same, so it's at -2 and then -4, right? Because 1/4, the reciprocal of 1/4 is 4 over 1, right? And because it's negative, it stays negative. So that allows me to get a pretty good sketch of my graph. I can find the slope between any two nice points. Again, that's why I kind of need this x-intercept and this other nice point, because a lot of the time my invariant points aren't nice. So if I go 1, 2, 3, 4 units down and 1 unit to the left, right? Or 4 units up and 1 unit to the right if you go the other way. This thing has a slope of 4. Y equals 4x plus b. It looks like I did a pretty good job of sketching where my y-intercept is. Oh, I actually don't think that's right. So that's why I'd recommend using the point. So I'm plugging this in, right? This is my x and my y. I'm going to plug it in to my x and my y. And so negative 4 equals 4 times negative 2 plus b. Negative 4 equals negative 8 plus b. I add the 8 to both sides. Okay, it was in the right spot. 4 equals b. So then y equals 4x plus 4. That's the equation of the linear function that causes this reciprocal. So again, this straight line would be 4x plus 4. We've studied those. We spent a lot of 10C looking at those. This curvy line would therefore have to be 1 over 4x plus 4.